The paper I'm proposing is Challenges and Opportunities in System-Level Evaluation of Photonics. The paper discusses advances in photonic components in high-performance computing, challenges imposed on system performance assessment, and proposes qualities for desired solutions. First, the authors introduce the emerging photonic technologies. Then a section follows that states the need for a systematic methodology to extract system-level models. Subsequent sections include an example of extracting architectural level metrics and various types of challenges in system-level assessment caused by photonic components. The final section describes qualities for desirable solution to the emerging photonic situation. The paper focuses on HPC systems, which have become increasingly pervasive in modern life. Many applications on HPC systems are data-intensive and place a lot of stress on the interconnection network. Compared to 2010, today's top 10 HPC systems have 65 times the compute throughput in floating point operations per second, but only 4.8 times the communication bandwidth. The ratio of the increase is 8 to 100 in bandwidth versus compute. In addition, communication could become the bottleneck in specialized computation. Google's TPU has a compute capacity of 90 tera operations per second and a peak off-board communication bandwidth of 34 gigabytes per second. Now, this means that data arriving on the TPU must be reused over 2,700 times so that computation on the TPU is saturated before communication. Recent advancements in photonics can provide promising solutions for future communication challenges and can break through the energy bandwidth limitations of conventional electronic interconnects. Photonics can provide high transmission capacity and low energy switching. Optical fibers of 100 gigabits per second are widely used, and those up to 400 gigabits per second are in development. Optical switches, such as those based on micro-electromechanical systems, array waveguide grating routers, or ring oscillators, are developed. Also, photonics can achieve very small energy per bit independent of distance, up to a maximum. While these qualities are attractive for networks, making optimal use of photonics requires rethinking the entire system architecture, including the software stack. Here, the authors list several reasons. First, optical switches has a reconfiguration delay. This is because they belong more to the circuit switching side of networking than packet switching. Second, computation cannot be performed in the optical domain. Third, simply replacing current network components with photonics cannot provide the advancements necessary for future systems. This is because current data center scale networks already consume little power, only 4% to 11% of the overall consumption. Therefore, the key idea here is to change system architecture to better make use of emerging photonics, and so system-level performance can be increased. Now, this requires accurate and scalable high-level system evaluations, which in turn require accurate system-level models of emerging photonic technologies. Note the emphasis on system level because, for example, evaluating optical fibers or switches in isolation does not provide accurate information for the system-wide impact of those technologies. In addition to models, system-level evaluations or simulations are also valuable to photonics developers because they give developers an understanding of how to best change their device for best system-level impact. As an example, the systematic impact of error rate on energy may motivate developers to focus on reducing errors, while on the device level, this correlation is not obvious. Current widely used simulators, such as SST and GEM5, can execute application code and include behavioral descriptions of important components from the system network, on-chip network, processors, accelerators, memories, caches, etc. They can also reveal high-level metrics such as application execution time, network load, memory usage, and so on to system architects. Regarding existing simulation tools, the authors argue that while support for photonic devices are being added, they are either not designed to perform detailed simulations or do not provide complete coverage for emerging technologies. Therefore, a systematic methodology to extract system-level models for any emerging photonic technology, including channel, switch, off-chip, or on-chip devices, is necessary. In the next section, the authors cite an example of extracting high-level performance and energy numbers from photonic device demonstrations. The metric used here is energy per bit, and the device in question is a transceiver plus laser source. The laser source power is considered around a number of factors, such as receiver sensitivity, bit rate, optical losses, and wall plug efficiency. This is added to the power consumption of the modulator driver and the receiver. Furthermore, if the transceiver is microring based, the power for tuning to the desired wavelength and locking on the wavelength is also added. These numbers are then translated to a system-level metric of power per bit, for which a formula is not given in the paper. In the next sections, two types of challenges are discussed, which complicates the system-level assessment of photonics. First, the challenges of network plane simulation. In this part, the issue about the differences of photonic networking versus traditional networking is raised. In contrast to the current predominant networking topology, which features a static physical network layer and implement decentralized routing, photonic networking derives its advantages from its reconfigurability. Furthermore, given the static network assumption, the established convention for system-level workflow are separated into two phases. The first phase is the system's architecture setup phase, where the general machine parameters are set up, and the second phase is actually where the simulations take place. This is displayed on the left side of the figure. On the right, however, is the more photonic-friendly simulation diagram proposed by the paper. The main difference is the separation of the physical and the logical topology construction. As the physical networking is obviously fixed, the reconfigurability of the photonic networking is then represented in the logical construction stage, which is part of the simulation procedure. In essence, networking construction is separated between setup time and runtime. In the view of the paper, this is the first step toward reflecting the physical reality of photonic networking. The next section focuses on software stack simulation challenges. The authors first argue that, given a fixed application, the details in the network stack can greatly impact the traffic model of an architecture simulation. In the example of Message Passing Interface, or MPI, the authors maintain that the Open MPI implements many transport layers for message matching and data movement, and in each transport layer, there are different protocols for data exchange. Therefore, for the same MPI application, there can be different traffic patterns given the low-level network implementation. Another example is made on the TCP/IP stack, where the distinction between packet switching and circuit switching is again brought up. In electrical switches, packet switching is implemented, and packets are subjected to congestion control. On the other hand, in optical switches, packets would require advanced reservations made in a circuit switching manner, and flows would rely on resource scheduling instead of congestion control. In this scenario, network management can also greatly impact traffic and the network experience. Next, the authors argue that simulation is best used as a co-design tool, where both the physical architecture and supporting software can be simultaneously developed. This paradigm has already seen success in embedded systems and should ideally be extended to address system-level challenges discussed earlier in this paper. A number of simulators are cited to demonstrate that although different tools exist to solve particular problems, there is not a simulation tool that provides a complete framework to tune all levels of the network stack together. And so the authors call for a solution for true co-design of network hardware and software stack. Finally, the point is made that network middleware cannot be agnostic to competing features such as broadband or wavelength selective switching, packet or flow level completion, and packet switching or flow level switch reconfiguration. Therefore, simulation tools must be flexible and move away from dominant assumptions and pre-existing designs. In the next and final section of the paper, the authors describe desirable qualities for a solution to the system-level challenges. First, the design and development process that resulted in the current system assessment and simulators need to be repeated for photonics. This requires the photonic device designers and system designers to work together. This also means that low-level metrics should be consistently translated to high-level metrics, with the aim of being added to simulation tools. As displayed in the table, to make design explorations more efficient, the translation between the two domains should be systematic and rapid. To make this happen, the authors propose that a design automation tool should be developed to scale device-level experiments up to block-level metrics. This can be realized through libraries that describe new architectures and common building blocks, so that new devices can be integrated into the system in a predictable manner, as shown in the figure below. In this figure, at the center where the device joins the architecture, the interaction of components need to be considered. This will require accurate modeling, but also there should be a synthesis step where metrics are optimized within constraints of the system. A necessary step in combining different models in high-level simulations is validation, since the simulation does not necessarily preserve the correct behavioral or energy models. The validations should be hierarchical, where small models are compared with physical simulations or device demonstrations, and larger simulations should consult design limitations, operating conditions, and so on. As the authors state, the value of this approach is to provide a fast and simple method to gauge system-level impact for emerging photonic devices, such that initial approximations can be made before more effort is spent to increase accuracy. And further, if the procedure maintains reconfigurability, accuracy, and can be extended to support future device types, then it can also be used to support future design methodologies, because early simulations of future devices can provide invaluable insight, as long as reasonably accurate models can be derived. In the final paragraphs of the paper, the authors makes an interesting parallel comparison of the photonic design domain to computer architecture design, where the development of Paradise enables the extraction of chip-level metrics given physical-level descriptions of emerging technologies. As this approach in computer design was successful, the authors are hopeful that it can also be applied to the photonics domain. In conclusion, the paper discusses the need to quickly integrate photonics in future systems, as well as the current challenges in extracting system-level metrics from device demonstration for photonics. It also makes the case for a systematic approach to bridge the gap between photonic device developers and system architects. This approach will accelerate adoption of photonic devices at the system scale and optimize system architecture to better match the strengths of photonic devices. This is the end of my presentation. Thank you.